because they are closely connected. Thank you. So let's go on the next and last presentation of the colloquium, actually, this time dealing with thermal cycling, but more in the solid states. Manas is one of the co-organizers of the symposium, so I think most of you know him, but he's currently at Polytechnique, and I then leave you the floor immediately, Manas.
Thank you, Roland, and thank you to the speakers before, because you have made my job a bit easier. So I'm Manas Upadhyay. I started as an assistant professor at Ecole Polytechnique circa 1 BC, which is now stands for before COVID, so 2 years ago. And I started getting interested into additive manufacturing just at that moment. And I asked the question that Damia posed, is rapid solidification additive manufacturing? And at that point, I was wondering whether that is indeed the case or not. And I thought maybe unlikely, but in many cases, yes, but in some cases, unlikely. And so I started exploring what I'm going to talk about, that is microstructure due to solid state thermal cycling during metal additive manufacturing. Okay, so to understand what is solid state thermal cycling, let's just take an example of deposition of a wall, and we focus on the thermal history that is experienced by a point X, as you can see here on the screen. Just after deposition, it solidifies rapidly in a few milliseconds. And then for the rest of the build cycle, it is subjected to thermal cycling in the solid state. Now, this thermal cycling occurs over a very long period of time at different temperature amplitudes and rates. As Damien and Charles-André have shown, there is a lot of research efforts that are being conducted on understanding how the rapid solidification results in the formation of the microstructure at this point, for instance. And the current understanding is that, okay, there is a lot of models and experiments being conducted, and they are being compared directly to what we get at the end of the manufacturing process. But there is not clearly at that point, and 2 years ago when I started working on this, there was no clear understanding of what could be happening or what is happening in the microstructure. So what could happen during solid state thermal cycling? Well, you could have different mechanisms that could occur. For instance, at the intragranular level, you can have dislocation dynamics, recovery, precipitation, microsegregation that could happen in the solid state. At the polycrystal level, you can see grain fragmentations, phase transformations, recrystallization, grain growth. And all of these can result in intragranular structure and stress evolution at this level, and texture morphology and intragranular stress evolution at that level. Which means that the as solidified microstructure that you get at the end of rapid solidification is not exactly the same as what you measure at the end of your building process, or what you observe at the end of the building process. Now, all these phenomena, these mechanisms and the microstructural changes and stresses are phenomena that are affected by SSTC, and they determine the mechanical response. And so, for instance, over here, you see this tensile strength versus elongation curve showing a large scatter in the mechanical properties from different machines and different materials. And maybe to understand this better, we need to focus a bit more on solid state thermal cycling. Going beyond that, if we understand solid state thermal cycling well enough, then we could harness it to tailor microstructures during additive manufacturing. For instance, we can propose in situ, in process and post-process thermomechanical treatments during additive manufacturing. Okay, so from an experimental standpoint, how can we study the role of solid state thermal cycling? Well, it's rather simple. You just compare before and after solid state thermal cycling state of microstructure. Of course, it's easier said than done. There are two ways to go about it. The first one is operando techniques, which we saw earlier this week, where you have sufficiently time-resolved equipment that you can use to measure the microstructure changes continuously as your additive manufacturing process proceeds. For example, using synchrotron XRD that Stephen showed, or radiography that Philip Withers showed. The other approach, which is less explored, is in situ and ex situ stop and start techniques, where you print a little, you extract samples, and then you continue printing, or you observe those samples and you continue printing and you continue observing them in a stop and start approach. And this is where microscopy could be useful. For instance, you can print 3D materials, 3D print materials, and then transport them to microscopy facilities, and then characterize their state, then perform in situ or ex situ SSTC, and then recharacterize. Now, the advantage of this is that you can dissect the temperature versus time curve to study the role of temperature, temperature rate, number, and type of cycles using microscopy. And so this is what I'm going to show you a bit about. On the modeling end, which is essentially my background, when I looked at 2 years ago at the current state of the art on modeling, I was surprised to find that there was no importance given to solid-state thermal cycling. The solidification models that went directly to microstructure prediction to properties modeling. So there was a huge gap in focusing on solid-state thermal cycling at that point of time. And so I decided to spend a year understanding what could we do on this. And I proposed an ERC project, and thankfully it got approved. So this is the starting grant, which started 4 months ago. And the topic is harnessing solid-state thermal cycling to guide microstructure evolution of additive manufactured metallic alloys. The acronym is GAMMA. Okay, so what are the aims and objectives of this project? Well, the aim is to first highlight the role of solid-state thermal cycling on microstructure evolution during metal additive manufacturing, and then show how, if and how we can harness it to design microstructures with desired material properties. And to achieve these aims, there are 3 main objectives. The first one is to develop new experimental equipments and perform the experiments. The second one is to develop and experimentally validate theoretical and fast numerical models, and then to use this experiment modeling synergy to engineer microstructures. So at this stage, I'm going to show you about the developments that we have been working on to understand the role of solid-state thermal cycling on microstructure evolution. Okay, so the focus is on developing models, simulations, performing simulations, and creating a synergy with experiments. And we are tackling the problem at the intergranular level and the polytechnique level. So at the intergranular level, we have used in situ transmission electron microscopy, ex situ transmission X-ray microscopy at synchrotron sources, and I am developing a thermomechanical dislocation dynamics model. At the polycrystal level, we are developing new techniques to do in situ scanning electron microscopy, operando and in situ synchrotron X-ray diffraction, and thermomechanical polycrystalline elastoviscoplasty models and simulations. So of course, I'm not doing this alone. I have a very, very great team with me. Nikhil Mohanan, who is a PhD student, Miriam Benhaj-Slama, Steve Godez, and Juan Guillermo Santos Macias, who are postdocs with me. And since we are working on developing modeling simulations and experiment synergy, well, I decided to call the group Moses, according to this title over here. Okay, so these are our activities. I'm going to split this talk into 2 parts. The first focuses on experiments. The second part focuses on modeling. The first experiment, which is with in situ TEM, is an application-based. The second one too, TXM, is application-based, and those are all developments. So let's start with the in situ transmission electron microscopy experiments that we did. This is the main project of Miriam. Okay, so why do we want to do in situ SSTC in TEM? Well, what we want to understand at the intergranular level is how dislocations are evolving, how precipitates, or how chemical heterogeneities are evolving. Of course, with TEM, we will not get information on stress evolution, but we can get information on structure evolution. Okay, so the aim is, the first step was to understand whether intracellular heterogeneities such as dislocations and precipitates could evolve during SSTC or not. The advantages of TEM are that you are getting an interatomic length scale resolution, so you can follow at a very high resolution changes, very minute changes. And we can characterize before and after SSTC states, so we can follow defect evolution and mass transport. And high vacuum implies that we have no oxidation. So that's a very big advantage because we are looking at very small samples and we want to avoid oxidation. And the biggest advantage was that this experimental setup is already available at a partner laboratory, which is MSS MAT in Central Supélec. And we worked with Eva Heripre and Luis Yedra, who is now at University of Barcelona. Okay, so as much as we are conscious of the advantages, we are also conscious of the disadvantages. And of course, the first question is, it's a thin film technique. What is the representativeness of this in the global scheme of additively manufactured materials? And the second disadvantage is that it is a destructive technique with a long preparation time. But we have solutions for that. Okay, so focusing on the experimental setup, the way we do this is we print our samples in the LMD machine that we have over here in our lab. Then we do an EBSD characterization to understand what is the grain structure, and then go to the FIB SEM that is installed at MSS Mat, where we prepare our lamella from an interesting zone that we figured out from the BSD maps. We put this lamella on this fusion in situ heating and thermal and electrical holder, which goes into this Titan 3 TEM, which allows us to study, with all these detectors, allows us to study the evolution of dislocations and precipitates, chemical heterogeneities. Now, the peculiarity of this fusion holder is that it allows us to go to temperatures up to 1200 degrees Celsius at a temperature rate maximum of 1 million Kelvin per second. So that's very nice. That's AM rates. And the disadvantage of this is that its tilt is literally 10 degrees, so we cannot really characterize dislocations. And our focus on this study was on chemical heterogeneity evolution. But we have figured out a way how to do the dislocation characterization as well. Okay, now we wanted to pick up a model material that has been very well studied in the literature so that we have quite a big background on what already exists and what new can be done. And we picked up 316L stainless steel naturally because it's one of the most studied materials that is relatively easier than, well, okay, I will not say easier, but it's a model material, which can be processed with directed energy deposition techniques and powder bed fusion techniques. So laser metal deposition and selective laser melting. And in both cases, we have hierarchical microstructures. At the polycrystalline level, we have columnar grains. So here is an example of a back and forth printing with this being the building direction. And you can see the grains quite well. There are some columnar grains with some bunches of equiaxed in between. We have at the intragranular level, if we zoom in, we have some dislocation structures that are formed, and they quite often overlap with chemical heterogeneities that are inside. So you have here microsegregations and some precipitates. Okay. Now, since we were focusing on the chemical heterogeneities, the best way to study them is to characterize them with EDS. So here are many different EDS studies that are done, and all of them agree that the microsegregations are molybdenum chromium rich cell walls, and the precipitates are all oxides, manganese silicon oxides. So we were expecting to see that. Okay, so what we did with the idea that we wanted to subject lamellae to additional thermal cycles, we first only printed a 3-layer wall and cut a cross section and took out 3 lamellae from it. And then we also printed a 60-layer wall and took out 2 lamellae from it. So in total, we had 5 lamellae in the beginning. And we put them all on this electrothermal chip holder to do the solid-state thermal cycling. We started looking at the first lamella, and we found there were 16 precipitates. These red ones are ones that we found after zooming in with high-resolution STEM mode. And we started characterizing those with bright field and dark field detectors. So this was the first precipitate that we characterized, and we found something very weird, that it had contrast everywhere that was different from the surrounding matrix. When we did the EDX characterization, we saw that, okay, there was only one part of it that was manganese silicon oxide. The rest turned out to be rich in molybdenum, chromium, phosphorus, and sulfur. Okay. Now, this is something that was unexpected for this material. As I mentioned before, the literature was consistent on saying that precipitates in additively manufactured material, 316L stainless steel, are only manganese silicon oxides. We look at the second precipitate, the exact same thing. There is a molybdenum, chromium, phosphorus-rich, sulfur-rich inclusion. Okay, at this point, we considered the possibility that there can be non-oxides present in additively manufactured 316L stainless steel. To prove that or to disprove that, we looked at all the 5 lamellae and identified 55 precipitates in them. We characterized all of them with EDX, all, and found that there were 16 oxides, 3 non-oxides, and 36 of them were mixed oxide and non-oxide precipitates. We did EDS line profile analysis on every one of them. In some cases, we had to do more than one line profile analysis. For instance, this one was quite complex, so we really did it a lot. We have, and we found that these non-oxides were sulfides, carbides, and phosphides, and in some cases intermetallics. And so at this point, we were like, okay, what is going on? There are 70% of these precipitates are non-oxides, but we shouldn't be seeing any non-oxides because it has never been reported. So what is the origin of these non-oxides? To do that, we did a precipitation kinetic analysis, which starts with understanding what is the size distribution of these non-oxides with respect to the oxides. So as you can see here, this is a size chart, and all these dashes are all the precipitates that were existing in these 5 lamellae. We looked at the average values of these precipitates. So this is only pure oxides, pure non-oxides, mixed oxides in mixed precipitates, and non-oxides in mixed precipitates. And you can see that consistently, the non-oxides are smaller than the oxides. Now, the next step was to do finite element simulations to understand what is the temperature versus time relationship along this microstructure as it's being built. So Nikhil did some simulations to find these temperature versus time curves at these point X, Y, and Z in our simulated geometry. And we found that, okay, there was an average temperature rate of 20,000 Kelvin per second that was being observed. And so we took all this information of the size and the temperature versus time curve and put it into a precipitation kinetics model, where we said that at 2 × 10⁴ Kelvin, which is this black curve, we should have a size of precipitates or non-oxide precipitates of the value that we saw here, which is this one. And we do that. We then started to perform simulations with the parameters that we fitted for different temperature rates. And we matched with 2 values that were given in the literature from experiments by Kim and co-workers. So when we saw that the parameters that we used from here were fitting very well, we said, okay, this kind of validates our finite element simulations and the precipitation kinetics simulations. Then we looked at what is the volume fraction that could be forming at different temperature rates. So the conclusion we drew from here is that non-oxides typically form at temperature rates less than 10⁵ Kelvin per second. Below that, it's quite small in diameter and very little in volume fraction. And during LMD, we see temperature rates that are typically of the order of 10⁵ or less. But during SLM, we have temperature rates that can go higher, up to 10⁶ or 10⁷. That could be the reason why we do not see them in SLM. So this work we recently published in Scientific Reports, and you can find it over there. Okay, so this was a little bit of a detour because we had to answer that question, but then we came back to our original study, which is in situ SSTC in TEM. And we wanted to understand what is the role of the maximum temperature, what is the role of number of cycles and the type of cycles, what is the role of the temperature rate, and the role of annealing that we could do as a post-process. Okay, so we started with the role of maximum temperature. We did 2 cycles at 4,000 Kelvin per second, up to 500 degrees, the first one, and the second one was up to 1,000 degrees. In general, the cycle up to 500 degrees Celsius brought negligible change in the microstructure in the TM lamella, but the cycle to 1,000 degrees brought significant changes. So in the cases of oxides, we saw that manganese started stripping away from the oxide and fusing into the matrix, leaving behind silicon and oxygen. There were some changes in silicon oxygen, but not as significant as those in manganese. There was only one non-oxide, pure non-oxide inside this lamella. So this one changed significantly in geometry. You can see here it's quite distorted compared to this, and this has resulted in a change in the chemical composition as well, of course. And in mixed precipitates, well, there were a bunch of different changes that were happening, but there was some commonality. So in general, the sulfur content was redistributing and decreasing. And manganese continued to rediffuse into the matrix in all these cases. So that was the case of maximum temperature. The next, we studied the role of number and type of cycles. So we did one cycle up to 1000 degrees at 4000 Kelvin per second, heating and cooling. And then we did the same first cycle, and then, but we continued doing cycling at lower temperature rates and amplitudes. So we have the same first cycle, but here now we have we have added more cycles here. So in general, there were more changes because of this additional cycling, but the biggest difference is we saw that Mn diffusion was happening from both oxides and non-oxides. We found that one of the oxides actually dissolved completely into the matrix. The content of molybdenum, which was originally not significant in these oxides, in fact started getting stripped away from the surrounding matrix, leaving behind the same molybdenum content inside this precipitate. So that was interesting. And then we started seeing coronas of chromium formed around oxides. Now, these were similar to the coronas that we saw forming, that were already present in the as-built material. So this was something that we found that, yes, it's a bit representative. Mixed oxides, we started seeing that these coronas were disappearing. Manganese chromium was beginning to decrease and redistribute, and both were concentrating in the same region. Phosphorus increases in general, and iron is encroaching onto the precipitate. So we thought that, okay, here the precipitate is shrinking in size. It's going to probably disappear at some point if we had continued. Okay, so the next was to study the role of temperature rate. We did 2 cycles up to 800 degrees Celsius on 2 different lamellae. One was at 4000 Kelvin per second, heating and cooling, and the other was 1000 Kelvin per second, heating and cooling. We saw there were more significant changes at 1000 Kelvin per second than at 4000, which makes sense because you would have, well, chemical elemental redistribution is a mass transport process and it takes time. So the more time you give it to the same temperature, the more it will change. We saw that there were formation of non-oxide precipitates on oxides at 1000 Kelvin per second. Again, much more than at 4000. There were, in the case of oxides, there was chromium ring formation and Mn diffusion into the matrix. So this is a common thing that happened every time. And in the mixed cases, we had diffusion of oxygen, silicon, and manganese into the matrix, and redistribution of molybdenum and chromium. Okay. Next, we studied the role of annealing. We did 2 tests for 1 hour each at 600 degrees Celsius and 700 degrees Celsius. So the 1 hour at 600 degrees Celsius brought no change at all. The 1 hour at 700 degrees Celsius brought significant changes. In fact, in the entire lamella, there was a redistribution of molybdenum and chromium, which was inside those cellular walls, solidification walls. It now redistributed into some very random microsegregations. All precipitates were showing small depletion zones in manganese, silicon, and oxygen. And there was an enrichment in molybdenum and chromium in general. So that was an interesting aspect of annealing, that it's trying to heal the material somehow by removing these heterogeneities. But because it's a thin lamella, it's creating these weird structures. So here, I think it could be it must be a artifact of this thin lamella. Okay. So at this point, I can draw some very general conclusions. The first one is, could intragranular heterogeneities evolve due to SSTUC during additive manufacturing? Yes, absolutely. We have seen dislocation dynamics as well. I have just not spoken of it here, but it definitely does. There is redistribution of elements in precipitates, shrinking of precipitates, and nucleation and growth of non-oxides on oxides. That's happening. And so we have this 2 publications. This one is being prepared and we will hopefully submit it in a couple of weeks. But the main challenge that everyone probably is thinking is, do we observe similar changes in bulk samples? Well, to answer this question brings me to the next part of the talk, which is ex situ transmission X-ray microscopy, which is being worked on by all 3 postdocs in the group because it's not an easy approach. Okay, so why are we doing transmission X-ray microscopy and where are we doing it? So we are doing it at the Anatomics Beamline in Soleil. It's a 3D nanotomography approach, which uses the Zernike phase contrast microscopy technique. So the way it works is you have a monochromatic X-ray beam that comes and it's focused on the sample. It interacts with different parts of the sample. So there is the homogeneous matrix part of this 316 cell steel and the precipitates that it interacts with in a different way. That results in a phase shift of part of the beam. And there is also the part of the beam that is unaffected. So there are three parts. One that is interacting with precipitates, one with the homogeneous matrix, and one with nothing. Then this phase ring is trying to increase the phase shifts such that there is destructive interference between parts of the signal that is coming out. And once that has happened, there is a detector that detects these phase shifts and reproduces them as brightness changes in the in the images. So the experiments we did were at 10 to, well, they have the capability to do it at 10 to 17 keV. We did it at 10 keV, and we will do it again at 17 keV. They have a field of view of this detector at 30 by 30 microns with a pixel size of as little as 45 nanometers and a resolution as low as 100 nanometers. So what we did is we made bulkier samples than TM lamellae. So we made these micropillars and we studied them with TXM. So here is this typical image that you would get out for this micropillar. You will have these ring artifacts that are forming, but you can clearly see the precipitates that are forming over here. These ring artifacts, we can remove them with post-processing treatment. So this is in the top down direction. And if you see the side view at a slice, you can see that these ring artifacts manifest as ghost precipitates, which are really not precipitates, they are just artifacts over here that are mirror imaged along this line. Okay, so we map them via TXM. Great. How do we perform solid thermal cycling on micropillars? Well, so this is where we did what the French call bricolage. We made our micropillars with the fib. Then we stuck them on this TEM electroheating holder. We went to Soleil, we did our TXM. Then we went to this TEM and we did heating and cooling on this. And we did a back and forth from Soleil to Santhal Supalek, even during night shifts, to do this experiment. Did it work? Yes, surprisingly it worked. Or rather unsurprisingly, because we were hoping that it works. We did SSTC experiments on 4 micropillars. So I'm going to show you one of the results of this one experiment. We did 4 tomographies on this one micropillar at different times of this cycling. So here you have the same micropillar that has been subjected to this cycle. And we have done tomography here, 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 and here. So this is the initial state. You can see a bunch of precipitates over here. This is the state after the first cycle. So this one, a single cycle, which did not result in significant changes. We didn't see anything that was different from this state. After this cycling, we saw some visible changes. So there were new precipitates that popped up. Some of them grew, some of them shrunk, some of them coalesced. Probably that was what we saw as growing. And after this annealing cycle, we saw very significant changes. Here, we have this as our reference point, and here you can see that the precipitates have completely vanished. New ones have appeared. It's a different story completely over here. Okay. So we are still analyzing these results, and hopefully soon we will have the results to a complete story over here. Now, why are we still analyzing it, and why is it taking so long? Is because the data analysis is a pain. One beam time results in 4 terabytes of data. And if you want to do manual segmentation of these precipitates, it takes hours. And there is only one parameter that you can use to do thresholding. So you have to spend hours and hours looking at these tiny dots. And it's prone to errors, of course. So instead, Steve has been working on machine learning-based segmentation algorithm, which is an automated technique, fast, more than one parameter. So you can look at the size of the precipitates, you can segment them accordingly. By segment, I mean identification, so figuring out where they are. And it's humans, which is a good thing and a bad thing in the sense that you avoid the errors, but you also probably may miss a couple of precipitates just because, well, it's a computer and not a human. Okay, the other challenge is during rapid solid state thermal cycling, the temperature that the chip that we use to heat the sample may not be the same as the temperature of the sample. And so there is an uncertainty in the amount of the heat transferred to the sample. And this was a challenge because we needed to find a way to solve this problem, and we did actually. Which brings me to the next part of the talk, in situ scanning electron microscopy. This is going to be the postdoc of Guillermo. So what we have done, and this was done from a different, this started from a different idea, is we have implemented a 200-watt continuous wave fiber laser inside our environmental SEM. We call this setup the laser SEM. So it's done, it's over here. It's installed, and Guillermo is already working on characterizing, well, doing experiments with it now. So what it can do is that it has the lasers, the possibility to tune it from 10 to 200 watts with a spot size varying from 20 microns. So we can do micropillars up to 500 microns. This also means that we can do material, we can do spot sizes of SLM type all the way to DED type. We have a scan area of 70 by 70 millimeter square, keeping the focus, always keeping the same spot size. So that's a large area. And we can have scan speeds of the order of 10⁻⁴ millimeter per second. So that's pretty large, and we can cover SLM and DED quite well with it. And of course, the ESEM has the possibility to incorporate both an EBSD detector and an infrared camera. So we can do temperature measurements and, well, EBSD. Okay, so this work has been mainly done in collaboration with this engineer, Alexandre Tanguy at LMS, who has worked with the design and implementation of this laser SEM. Okay, so what are the advantages of this? Well, if you want to do SSTC and microscopy, the current state of the art at that time was you do your EBSD characterization, you take your sample to the AM machine, you scan it with the laser, you come back and you remeasure. Well, instead of that, you avoid transporting samples, you do it in situ, and you don't oxidize it because you are keeping it in vacuum. You can do in situ EBSD, high resolution DIC, and temperature measurements with the equipment we have. As I mentioned, you reduce oxidation risk by doing it under vacuum and inert gas because it's an environmental SEM. And we can test different sample geometries, including micropillars. And we can test different materials made from DED and PBF. Okay, so the new way to do ex situ SSTC transmission X-ray microscopy is instead of doing this, this chip-based approach, we do the laser SEM-based approach where we prepare micropillars, go to Soleil, do the TXM, go to our laser SEM, subject it inside a controlled environment to a laser spot that is designed specifically to tackle this kind of problems, and then go back to Soleil and back and forth as much as we want. Okay. Finally, we also want to do synchrotron X-ray diffraction because, well, we are developing models that will predict the mechanical response, and you want to compare with strain measurements and texture evolution and other things. So we have also been working on developing this approach with Steve Godez, who is leading this, this development. Okay, so we have designed a mini laser metal deposition machine for synchrotron studies. This machine is 1 meter in height by 50 centimeters by 50 centimeters, equipped with a 1 kilowatt continuous wave fiber laser. It has, the substrate has X, Y, Z motion. The focusing head has Y and Z motion. So we can do a combination of different techniques, printing techniques. The laser at the nozzle has a rotation axis. So it can always follow the direction of printing. So if you're going this way, the laser is here, then it rotates 180 degrees, and then it's here like that. The print area is 140 by 140 millimeters, and we can print samples in any direction we want. Or for X-ray diffraction, we will keep it in this direction, but I'll tell you the advantage later. The max sample dimensions will vary from 0.6 to 10 millimeters in the X direction, which is this direction, 100 millimeters in the Y, and 30 millimeters in the Z direction. So it's pretty large samples. The substrate is water cooled, so we have a constant temperature, which is great modeling because we can have at least one Dirichlet boundary condition. The X-rays will be coming in from this direction. They will interact with the material, and we have wide and tall captain windows at the exit, which allows us to have a large diffraction angle. The thing is hermetically sealed, and there is an argon inlet and outlet so that we can do everything under inert gas, and we have control over almost everything inside. Okay, so this has been realized after 1 year of discussions and construction with Hakim Garbi, who is also an engineer at LMS, who has dedicated a lot of time and effort to this machine. And we have discussed with people at Soleil, PSI, so Stephen is here from PSI. We have discussed a lot with him at ESRF and at Petra. Okay, so this is the photo of the machine taken yesterday, and it's 2 weeks away from being completed. This is just some wire management to be done, but otherwise it's working, and they are currently testing everything over here. Our intended use for this is to do synchrotron X-ray powder diffraction, high resolution reciprocal space mapping, which allows us to, which is a diffraction technique that allows us to focus on one grain in the bulk of the material, operando, sorry, not operando, in situ. We want to do operando radiography with it. We can. It's designed for that. It is also designed to do neutron diffraction in both transmission and reflection mode. And we can discuss this later, how that is possible. So with the 1 kilowatt laser and 6 motion axis, we have different printing parameters and strategies that are possible. The hermetic sealing with argon gas allows us to do titanium and aluminum alloys together with steels and nickel-based alloys, of course. And the large captain window with high energy X-rays, which will allow us to map many different peaks, to measure many different HKL peaks. And we have a bunch of safety measures around it. And we have 2 experiments scheduled in fall 2021. So we are looking forward to this. Okay. So here, so far I have talked about what applications and developments we have been doing with the experiments. And one of the objectives of these experiments is also to help validate the models that, well, I'm very interested in developing. And it's also my background, so I love developing models. So what are the modeling activities that we have been doing along with these experimental developments? So the first one, well, as I mentioned, that we are missing currently models dedicated to understanding solid-state thermal cycling. And so what we want to do is we want to stretch this graph a bit and squeeze in some space for solid-state thermal cycling response prediction. So we want to take input from solidification models and use a coupled heat conduction dislocation dynamics and a coupled heat conduction crystal plasticity to study how it would evolve, and then use the same framework to do properties modeling. The trick is that we want to use a modeling framework that allows us to do both at the same time with the same model. We just have to switch a switch, essentially. We have to toggle a switch. And so that is a challenging thing, because how do you do that? How do you put everything in a single framework? Well, let's see. So this has been my focus, thermomechanical application model, dynamics theory and simulation development. Okay, what do we want the dislocation dynamics model to do? We want this model to, well, it is a single crystal model right now. And we want it to be driven by a thermomechanical driving forces such that it can predict temperature changes as well as dislocation dynamics and their coupling. Next, we want this model to be able to extend it to elastically heterogeneous domains so we can study dislocation interactions with grain boundaries. We want the model to be coupled with chemical species evolution, for instance, phase field modeling to study precipitate evolution. And we want to numerically implement it so that we can run simulations at experimental timescales. Finally, we want to upscale the model to crystal plasticity level so that we can connect it with, well, we can predict crystal plasticity, well, thermomechanical fields at that level, and connect with models of recrystallization and grain growth. Okay, so it's a lofty dream, but is it realizable? Yes, there is a way. We can use a continuous representation of dislocations, and we can use time-explicit Runge-Kutta discontinuous Galerkin finite element approaches to solve the problem. Okay, so what do I mean by representing dislocations continuously in a continuum? Most of you would know that there are one of the most common ways to use to represent dislocations is as a line defect, singular line defect. And this has started more than a century ago, from initial works by Michel Tempe to Volterra to recently by Hertha-Lotte and all the people that have done discrete dislocation dynamics after. Another approach is to smear out this dislocation line and this singularity into a finite, from an infinite singularity to a finite volume, and then represent the dislocation via a finite non-zero polar dislocation density, which you characterize it as follows. So this dislocation density is a function of the dislocation character divided by the volume of the sphere that you, or the cylinder or whatever that you use as your averaging domain or as your smearing domain. And so this idea started with the work of Nye and Kroner and Mura and Willis, and all the way now to the Acharya group, which has worked extensively on it from 2001 to 2020. So this dislocation character is taking into account the Burgers vector of the dislocation, of course, which is constant normally along the dislocation line, and the line direction at that point. So of course, this line direction would change as you go at different points. The advantage of using the continuous representation, besides everything I mentioned before, is also that in the limit condition, you can recreate the discrete representation. Okay, so I'm going to rush through 50 years of research work and present to you the isothermal and adiabatic elastoplastic dynamic theory of dislocation fields. So at the core of it lies this these equations. You have the curl of the elastic distortion, which is equal to the dislocation density, which is equal to the negative curl of the plastic distortion. And the divergence of alpha is equal to 0. So what this says, this is that dislocations cannot end inside the material or at the bound, they can be present either as loops or end at boundaries of the domain or end at each other. This equation essentially tells you that it's a solenoidal field. So it is divergence free because the divergence of curl is equal to 0. Equation is the transport of dislocations. For a slip system beta, let's say you have alpha dot equal to minus curl of u dot p, and u dot p is alpha cross v. So this is the plastic slip rate. This has relationship with the Oro-1 law. The velocity of the dislocation is prescribed constitutively from a dissipative relationship. So you have to respect this relationship, and essentially any expression for v that respects this relationship is admissible. S is a source term for dislocations, where you can have, for instance, point sources, or it could be thermal sources, whatever. And then the rest of this model is just standard dynamic equilibrium, elastic constitutive law, and Dirichlet-Neumann boundary conditions. So this was until 2001. And Roland, am I running out of time? Yeah.
Soon, yes. So
okay.
I don't know how many slides you have left, but maybe you try to accelerate just a little bit.
Yes. Okay. So this approach then, Acharya then showed the approach where you can uniquely decompose this tensor, the elastic distortion tensor, into compatible and incompatible parts. And given an alpha from experiments, typically, you can uniquely obtain the elastic distortion out of this following this procedure over here. The details are in my paper, I will, which is published over here. So when I combine this together in a strong coupling with heat conduction, this is the model that I get. All these red parts are the new additions to the model. You have the contribution of the thermal changes into the dislocation density, and the evolution of dislocation density field. And you have temperature changes that occur due to plastic distortion evolution and plastic strain evolution. And then these are the elastic laws and the dissipative law that you can, the Fourier law of heat conduction that you get out from energetic and dissipative analysis. So to just conclude on these predictive capabilities, with these equations, you can show that with the absence of dislocations, if there are any temperature changes, they will result in the evolution of alpha and elastic distortion. That means without presence of dislocations, temperature changes can be accommodated by stresses that are generated in the material. In the presence of dislocations, temperature changes can be accommodated by dislocation density evolution without changing the stress field. So now you can have dislocation structures that could form during rapid cooling without changing the stress field at all. This is allowed. It doesn't mean that it happens all the time. And this equation shows that dislocation dynamics results in local temperature changes. Okay, so I did a numerical implementation of this with the Runge-Kutta discontinuous Galerkin scheme. It took me 4 months to get to this point, and I'm quite happy. This is a very nasty formulation, but we got here and we did an annihilation simulation. So these are the parameters of these simulation. The key point here is that the simulation time was 1 second in 1,000 time steps of 10 raised to minus 3 seconds. This is the experimental point of view here that I want to give you, that this is what we were targeting, to do it at experimental time scales. And here is the simulation. Now, I think you can see it. What you see is that it started with this width and it maintains this width all the way. That means there is no spurious diffusion of the solution. And here you see these two dislocations are annihilating. And at the end, we get a residual of 10 raised to minus 12, the relative error of 10 raised to minus 10. So it's a very, very stable and good final solution. Okay, I will skip this part on upscalability because it's still work in progress, but essentially we can upscale this model to the crystal plasticity level by incorporating this plastic constitutive law. And that is the work of Nikhil Mohanan, who is working on that right now to upscale this model. He has already implemented, and we are now working on polycrystal simulation implementation. I have rushed through the last part a bit, but I want to take this time to acknowledge all the partners, the Moses Research Group, without which it would not have been possible, the 2 new students which are starting in 3 months, but they have already started working on their project. The technical staff here is outstanding at LMS, and all the researchers that you have discussed and contributed and collaborated with. Thank you very much. And these are the published works.
Thanks a lot, Manas. So I think because it was really a nice overview of both actually experimental activities and development of simulations. I think because we didn't have much time for any of the talks for questions, we might take some time now to answer questions for all of them, actually, for all 3 presentations, if you agree. So I see already that Stephen has one question. Yes, Stephen.
I have to let permission, sorry. Just a second.
Oh, yes. Everybody is still
yes.
mute, maybe.
Yeah, now everyone can. Sorry.
Okay.
Okay, yeah, thanks. Yeah, thanks, Manas, for this nice presentation. I'm happy to see how you embrace experiments completely now in your scientific career. I love it. Just a very short technical question. When you do the nanotomography to look at these precipitates, what exactly are you looking for? That was not clear to me. So, like, you can observe them, okay? Like, is it just like looking at them growing, and is your resolution good enough for seeing that with this kind of pixel size that you have?
Yeah, so that's a very good question, because we were wondering the same. There are a bunch of precipitates that are smaller than 100 nanometers in size, and quite a few that are more. And we actually see quite a large density of precipitates. So if you see here, you can see that you can already see these precipitates inside in this slice. And this is at 100 nanometer resolution already. So in DED, you would see these kind of precipitates having an average size greater than 100 nanometers. So you would at least in 1 pixel have them. And here we are having them in more than 1 pixel. And now in terms of what we want to observe is, we see actually that there is a 3D displacement of these precipitates. There is coagulation, there is dissolution. So we are assuming it's coagulation dissolution because it's disappearance, and or those are moving close together. They're moving closer to the walls of the micropillar, so there are surface effects. We're seeing all these things in our experiments. Right. Does that answer your question a bit? Yeah.
Yes, I think so, yeah. So, but you are limited to, so it's basically quite complementary to the TM work then, in the size range.
Except that it's a bulkier sample. Yeah.
Right. Yeah.
And this is a limitation also of anatomics. If you go to BM32 in ESRF, you get a much higher resolution. You go to APS, or Diamond, it's much, much higher. So this is just to see if our technique works or not.
You mean in terms of pixel size? You can go much
lower?
lower?
Resolution. They go down to 50 nanometers resolution. Pixel size is 22 there.
Right. Okay.
Yeah.
Yeah. And this is something that you can then also model? I mean, that's the idea then at the end of the day?
Yeah, so the lofty idea here is to use this as an input to dislocation dynamics models, where you can then simulate dislocation interactions with precipitates. We have a 3D structure, initial state available to us. Of course, we also want to give it to people who do precipitate evolution modeling.
Yeah, I was more thinking of that, yeah.
Yeah, but for our purposes, it would be for dislocation dynamics ones.
Right, yeah. Okay, thanks.
Maybe one complementary question to that. I'm just wondering, we have tried by different means to recrystallize this stainless steel after additive manufacturing. And we noticed that even though you have some significant dislocation density, sometimes it's difficult to recrystallize it. I was just wondering if you think it's might be due to the particular precipitate structures.
So it depends on the energy that is input into the material. I would say that these structures are so highly, it takes a lot of energy to move them or change them probably. And if you're annealing it, if you're recrystallizing it at temperatures that are very high for a very long time, you might see some changes.
Oh, okay, yeah, it depends on their stability, of course, depending on we do a heat treatment after additive manufacturing, and very often it's kind of difficult to move the boundaries. So I was just wondering if there is any pinning that might be specific to those microstructures after additive manufacturing. But...
So that's something we would like to study with this setup here. The laser SEM is to see how much can we actually bring local changes about in the microstructure with the laser.
Great. Yeah, that's really looks nice. Aude has a question.
Yeah. Thank you, Manas. Very, very impressive work and perspectives also. Looking forward to everything you'll be able to do with that. I had a question related to your mentioning of the neutron diffraction. So you're planning to look at residual stresses maybe, or is that what you have in mind? Or
so yeah, what I said is that we can look at do it in both transmission and reflection mode. And the reason why I say that is we will have, instead of captain, we can remove the captain and use aluminum walls. And if we use aluminum, then it's thin walls, then it's practically invisible to the neutrons. Then you can set it up in such a way that you print at 45 degrees and you can study intermittent start and stop diffraction measurements. So while building in either mode. And then of course you can do at the end of the build a residual stress measurement for the whole thing. But here you can focus on a region or on a layer and study on that layer as you continue building how the stresses evolve. So that's one of the ideas.
You mean the stresses and also see the lattice distortions.
Yeah, that's what I mean. Like what we observe from diffraction is peak shifts, peak intensity evolution.
Very nice. We'll need to think about that.
So, yeah.
I'll think about what you're built.
One thing that I want to mention is the reason I'm showing all of this right now is also to say that in a couple of years we are hoping to be capable to collaborate with all of you because we will not be able to study everything, of course. So the intention is also to work with colleagues and study your materials of interest. And that's why we are designing things that are as generic as possible.
So it's a bit the equivalent of the...
Just on this.
Sorry. Yeah, go ahead, Stephen.
Well, I was just wanted to ask in terms of this residual stress measurements. If you wanted to measure the stresses, you have to measure the strain, all strain components, right? How do you measure the one along the build direction?
You remove the sample, you take the machine out, and then you...
Okay. Okay.
It's near perfect.
You're asking too much here. Come on.
But I don't know. I mean, if you could tilt your machine by 45 degrees in the forward, like then it would work, right?
I think there is a bunch of problems with doing that. Yeah.
Yes. Okay. But
yeah, and all their difficulties, you'll need references, but I guess that is a solvable problem.
So it's meant to be a bit the equivalent of the mini SLM machine that Stephen presented, but on a DED side, if I understand.
Yes, exactly.
Yes.
Yes. Yes. And it's actually thanks to Stephen that we had a lot of discussions where I said, oh, what if we do this? And he said, no, you can't do this.
Great.
Yeah.
Okay. Any other questions, whether it is on this last presentation, on the last, or on the last two, the previous two ones?